Very good morning, my dear students. Today we are going to focus on fundamentals of fluid and fluid properties under the course Fluid Mechanics for Chemical Engineering. Our presentation sequence follows a general introduction and the objective of this presentation, and it again follows the definition of a fluid, which covers the complete understanding of a fluid and along with the concepts of shear stress and the difference between the classification of fluids as liquids and gases and the various types of fluids. And later on we are going to focus on the engineering units, which is the fundamental for measurement of fluid and fluid properties. And later we are going to focus on the specific fluid properties beyond the importance of density and viscosity. We are going to focus on the vapor pressure, the engineering significance of vapor pressure, the surface tension, and the capillarity. And finally, our presentation summary will end this session. Let us move on to the introduction part. Fluid mechanics. It is a study on the behavior of fluids, either at rest as fluid statics or in a motion as fluid dynamics, which includes the kinematics also. The particular analysis of fluid mechanics is based on the fundamental laws of mechanics, such as the Newton's second and third law is specifically applied here, along with the conservation of mass and energy, which includes the force and momentum. And later, an understanding of the properties and behavior of fluids at rest as well as in motion is of great importance in engineering, because without fluid and fluid dynamics, we can't imagine that we are living here, because that is how every fluid in and around us, by considering us as a system, is important to live in this planet Earth. The objective of this presentation is to identify the units of basic quantities which describes the fluid mechanics, such as the mass, length, time, and the force. If possible, we may have to consider the temperature and properly setting up the equations to ensure the consistency of units and defining the basic fluid properties. Later, moving on to the proper relationship which relates all the fluid properties, and we are going to focus on some simple examples by using those relationships. All right. Let us move on to the definition of fluid. Fluid. Basically, it is defined as a substance or a matter which undergoes deformation continuously when it is being subjected to a shear stress of any magnitude, which means even a pinch will disturb a substance or a matter that undergoes deformation, which means that undergoes the change in size and shape, and those substances are said to be fluid. Or in other words, it can flow continuously as a result of shearing action. And this includes any liquid or gases. And particularly if you consider the fluid mechanics, which is a division in applied mechanics related to the behavior of this liquid or gas, which is either in rest or in motion. And as I mentioned earlier, the study related to the fluid in rest or stationary is referred to fluid static. Otherwise, it is referred as a fluid dynamics, which also includes the kinematic part. The kinematic part is the application of your law of conservation of mass, and the dynamic includes the continuation of the application of law of conservation mass towards the law of conservation of mechanical energy in the flowing fluid. Got it? And very clearly I told about the definition. And one more thing is, it is a substance which deforms continuously or flows when subjected to a shearing force. In fact, if a shearing stress is acting on a fluid, it will flow, and if a fluid is at a rest, there is no shear stress acting on it. That is how it is being indicated in a simple way with arrowheads. Fluid is flowing means yes, there is a shear stress. The fluid is under rest means there is no shear stress. Thus, with the exception of solids, any other matters can be categorized as fluid. In a microscopic point of view, which means in a micron size or in our microscopic studies, the concept of the definition of fluid corresponds to loose or very loose bonding between molecules of liquids or gas. Got it? And the typical examples that we use in our engineering application, as well as uh, without these, such as the water, oil, or air, we cannot survive in this planet Earth, or we cannot think about our every second of our life. The concept of the fluid. In fluid, the molecules can move freely, but are constrained to a, we say it as a traction force, and which is called the cohesion. This force is interchangeable from one molecule to another. Say for gases, it is very weak, which enables the gas to disintegrate. Disintegration means the molecules will move far away where it is being contained. And for liquids, this cohesion force is strongest, which is sufficient enough to hold the molecule together, which means the space between the molecules are not far enough like gases. Got it? And can withstand high compression, which is suitable for application such as hydraulic fluid. The best example is we may use the engine oils or specific oils as a hydraulic fluid, which gives the smoothness functioning of the hydraulics. So, such liquids on the surface, the cohesion forms a resultant force direct into the liquid region. Say the direction depends on the point or the direction of force applied, and the maximum the direction distraction will be a perpendicular one, and the combination of cohesion forces between adjacent molecules from a tension membrane known as the free surface. Generally, the liquids and gases, a simple way to differentiate is every liquid has its own free surface because of a stronger cohesion. But for gases, it can't be because it is very weak. The cohesion force is very weak, and the molecules may move far away here and there, and completely it will fill sometimes where it is being holded or contained. So this is the primary difference between a liquid and a gas by the concept of the cohesion force and by the concept of the free surface. Like it was shown here, if you see the solids, you can imagine that molecules can be fictiously linked to each other with springs, which means the molecules are organized, the atoms or the molecules in a solid are organized random, and they follow a bonding nature, and those bonds, physical bonds, are very stronger in solids. That's why they undergo, we can't say every solid is rigid, because some of the solids are said to be the elastic body or the real solids. They undergo a deformation, change in size and shape based on the force applied or the load acting on it. So that's why they fictitiously link to each other with springs. Springs are the concepts of uh, elasticity or elastic deformation, when they are subject to a force, they undergo deformation, and if the force is released, they come back to their original position. uh, Likewise, the when you see an elastic rubber band, it works on the same way. This is the simplest way to understand what a solid is. But when you come for the fluid, it is being simply categorized as either a liquid or a gas. So now you check in the liquid in the same figure, which compares with the solid and gases. All the liquids exhibits a free surface, as I mentioned in the previous slide, because of the stronger cohesion. Okay, see the molecules. They move in all the possible direction where they have been contained, and the existence of free surface and the simplest pressure or the force acting on the free surface, it depends on whether the container or the vessel which is open or closed one. Say for example, if the vessel is open, means always an atmospheric pressure will act on the free surface. Okay, and according to the simple Pascal's law, the pressure is uniformly distributed and the pressure gradient is constant on the free surface. Got it? If you see the gases, see the molecules are free to expand and free to move. So the cohesion will be between the molecules will be very very weak or very very less, we can say. And moreover, the gases in a closed vessel can be holded good or can be compressed good. If you hold it in a open vessel, they will spill out. Sometimes most of the gases are not visible, but we can feel it with our common senses. Got it? So this is the primary difference between the solid and the fluid, particularly under the category of fluid, the difference between the liquid and gases in a simplest way to understand the concept of the fluid. Now, we are moving into the concept of the shear stress. As I mentioned before, there is no shear stress in a static fluid. Always when a force is acting on a fluid means the shear force will account in the direction perpendicular to the applied force. This is the fundamental concept of physics to understand the nature or the direction of motion. So if fluid is in motion, then shear stress are developed if the particles of fluid move relative to each other, which means the adjacent particles have different velocities, causing the shape of the fluid to become distorted. So, if you look into the picture, imagine that the bottom surface is a fixed one, like a river bed. Okay, so now the fluid is moving like the river water flow. So if you imagine that if you are standing on the river, always the bottom of the foot will feel that there is no flow current of water in a river, which means the velocity near the fixed surface is zero. And if you move a little above with the bottom of your foot, which is grounding on the river, and when you move from your bottom of the foot towards the level of water that you feel while standing on a known depth of water flow in the river, then above the foot, bottom of the foot, you will feel the flow current step by step. And when it comes to the free surface, you can feel that is the maximum velocity of flow of water in that river, which means the fluid particles will move at a different velocities with respect to the position. Say what I said, if you feel you are standing in a river means you can feel the movement of the fluid, water flow, movement of the water and the water particles, which is raising its velocity from the bottom of the foot where you have been grounded on the fixed surface of river bed step by step, which means a gradual increase in the fluid velocity you may feel. That is said to be, on the other hand, the velocity of the fluid is same at every point, means no shear stress will produce. The fluid particles are at rest related to each other. That you can feel at the fixed surface, like I mentioned on the bottom of the river. Got it? So, because of the shear only, a natural flow of water in a river, even we can feel it. Likewise, only whenever a fluid is under motion through any system, which may be open or closed, uh, all the movements because of the shear only. That's why we will focus on the velocity distribution, either the fluid under motion in a open channel or in a closed channel. Got it? Now, this slide is shows the exact difference between the liquids and gases, which I have focused already. Liquids, if you see, a free surface is formed if the volume of container is greater than the liquid, the third one. But for gases, they completely fill the vessel so that no free surface is formed. Sometimes they may come out of the vessels also, they spill out. Likewise, if you want to compress a fluid means the major application belongs to the compression of gases only, because gases are easy to compress. So the changes of volume is large, cannot normally be neglected, and this change in volume is directly related to temperature. Say, excuse me. If you are known about the ideal gas law, we call it as a perfect gas law. Generally, pressure is inversely proportional to volume or directly proportional to temperature. If you see that one, the change in volume means volume is also directly proportional to temperature. So, whenever we focus on the gases, they are easily compressible, and most of the gases are compressible and said to be the compressible fluids. Got it? So the change in volume during the compression can be related to the temperature. So the effect of temperature will be more focused on the gases and the gaseous processes. But when you see in the liquid, we can't able to compress it, because when you compress it, it will simply spill out on all directions, and that's why the liquids are said to be incompressible. Generally, all the liquids are incompressible. Got it? And mostly, when you see the uh, in a fixed volume, the liquid will occupies and takes the shape of the container. But for gases, there is no fixed volume. It changes volume to expand or to compress to fill the containing vessels where it has been processed. And if you see the examples, we can openly say the mother of all liquid is water, because we are surrounded by two-thirds of water with one-third of land in our planet Earth. Likewise, only our body is also designed by the nature or by the God to understand the same. Our bodies also will have the same future, which is completely having a two-third of fluid uh, within our body, and one-third is our skin, bone, and other things and all. Likewise, the mother of all gases, if you say, the air we breathe, okay, because the breathable or the oxygen, I can say, the hidden concept of mother in the gases. Without the oxygen, we cannot survive. in this planet Earth. That's why we generally say the mother of all liquids is water and mother of all gases is air, because both have the oxygen. So oxygen is the source of everything to energize our body, as well as to energize any fuel uh, when we use it for, say, for combustion to produce the all energy in another form, say the conversion of one form of energy to another energy. Got it? So these are the good way to understand the difference between the fluid and solid. Now we are moving on to the concept of understanding a fluid based on the law of physics. The godfather of physics is Sir Isaac Newton. He is the man who gave a most important type of fluid as a Newtonian fluid and non-Newtonian fluid, which means with his application of second and third law, he gave a law to understand what a fluid is, and we call that law as Newton's law of viscosity. It's an application of both the second and third law, and it says that our shear stress is directly proportional to the rate of shear strain, and we call it as a velocity gradient. And the proportionality constant is said to be uh, the viscosity of fluid, or sometimes we may say it as a dynamic viscosity of fluid. So, if you want to say a fluid is Newtonian, means it must obey this law, which means if you simply think this law uh, in relationship with the mathematical equation for a straight line, say the linearity, this equation exactly fits with a straight line passing through origin. Got it? That means if you plot a simple graph between the variation of shear stress along with the variation of the rate of shear strain, that is your velocity gradient, in the y and x axis, okay, a fluid which follows Newtonian means it exhibits a definite straight line passing through origin with a slope of its own viscosity. See, if you want to say a fluid is existing, means it must have a density first, because the density will always decide the action on the fluid, because you all will aware that density accounts both the mass and volume as a ratio. Okay, then if you want to say the fluid is a real, means then all the fluid must possess viscosity, which means they have to either obey the Newton's law in a linear manner, or they can do not obey the Newton's law and forms a non-linear relationship, means they are said to be Newtonian and non-Newtonian fluids. Because this is the category of fluid, uh, or categorization of a fluid after understanding what a fluid and a real fluid is. Got it? Okay. So whenever a fluid is said to be a Newtonian fluid, means it must have to obey the Newton's law of viscosity. And some of the examples are, as I said, the essential fluids which make us to survive in this planet Earth: air, water, and of course, without oil, we cannot think about what we are cooking and eating. And some other gasoline, kerosene, they are the essential for running our automobiles. And glycerin, benzene are our essential chemical. You can understand what is the benefits of those. And of course, the alcohol. Nowadays, everything is ruined by alcohols and alcohol-related chemicals only. All those comes under the category of obeying the Newton's law of viscosity. That is why the viscosity is a function only on the condition of fluid, particularly its temperature. Whenever the temperature of a fluid changes, definitely viscosity changes. Likewise, the compression we see, no, for the gases, volume change in volume is affected by the temperature. And when you say a Newtonian fluid, the magnitude of the velocity gradient, see the du by dy, how do you account it? Change in velocity along the change in distance or the position where we measured that velocity. Got it? That has no effect on the magnitude of viscosity. Only the shear stress matters a lot here to measure the viscosity, it seems. Got it? Now, as I mentioned, if a fluid doesn't obey, which means it's break its linearity, like a straight line passing through origin, if it breaks, say, if you have a straight line with an y-intercept or a curve with the concave upward or concave downward as a non-linearity in a relationship with the shear stress and the rate of shear strain, then such fluids are said to be non-Newtonian fluids. Here, the viscosity is completely dependent on the velocity gradient because it varies as well as the condition of the fluid. Okay, as I already mentioned, Newtonian fluids definitely follows a linear relationship with and concept of beginning from origin. So the slope is constant, which means the viscosity is constant for Newtonian fluids. When you see the non-Newtonian fluids, they always exhibit like a straight line passing or having a y-intercept, which means they need an initial stress to move and follow as a straight line. Or they may have a nonlinear curves like a concave upward and concave downward, which begins from the origin. Such variation in the plane geometry is said to be the non-Newtonian fluids behavior. Here you can see a simple plot which accounts both your Newtonian and non-Newtonian fluids. As I mentioned already, if you are having a data, a recorded data or an observed data between how the shear stress will influence in the rate of shear strain, then you can make out this plot. Got it? So already I strongly highlighted about the Newtonian fluid, which is exhibits a straight line passing through origin in such a plot. Now let us focus on to the non-Newtonian fluids. See the first one, the Bingham plastic. As I mentioned, it is a straight line having an y-intercept. Got it? Which means it needs an initial stress to flow continuously. Which means it resists a small shear stress but flow easily under large shear stress. Example is the best thing you can say is our toothpaste, which comes in a tube. Okay, so what we do is when we open the paste tube of the paste, okay, then we have to press anywhere in between its bottom edge to the mouth. So if you press only, it will fall on your brush smoothly later on. Likewise, when you squeeze out ketchup from a bottle, imagine that ketchup or a sauce where we add in pizzas or in burgers or whatever it is, you can see that one. Then it will fall very smoothly on it. Likewise, the jellies. Okay, these are our day-to-day life. We are seeing it. When we see in an engineering aspect, of course, this you can see, this example, sewage sludge you can see even in your household sanitation. Sometimes you may get blocked. So we need to push it out with a long stick or some other agents we have to add. Afterwards, only it regularly moves on our sanitation line and goes to either our septic tank or in a common area for where the sewage treatment is done by the municipality or the metropolitan areas. Got it? Then you focus on the pseudo plastic. See, the curve, how we describe is like a concave downward curve. We cannot say it as upward one, okay, because it is raising, okay, a somewhat a stream, and later it moves like a curve. And for a large shear stresses, almost it becomes a constant, which means for a concave upward curves, in general, if you measure the slope at any point or along various points on the curve, viscosity decreases with increasing velocity gradient or the shear stress. Got it? So most of the non-Newtonian fluids will generally falls under this group, like the milk we are using to make a tea or a coffee or a plain thing we can eat, and the clay which we use for like a binding agent, even to construct a wall for our houses in ancient days, they use it, the clay, along with the water. And nowadays, the modern construction uses the cement. Got it? So these are the good example to understand the pseudoplasty, which means most of the colloidal substances where the solids are suspended in a huge volume of liquids will cover the examples for this pseudoplastic. Got it? Then, if you see the bottommost curve, the dilaton, which is concave upward one by the mathematics, that means the viscosity decreases with increase in velocity gradient. So there is a specific category of some fluids in which the liquids volume are very less when compared to the suspended solids. What I am saying is in pseudoplastics, colloidal substances in which the volume of the liquids are more when compared to the solids which are suspended like a grains. But in dilatants, the composition or the volume of the liquids in similar substances is very less. That's why we say the dilatants, if you means the quicksands or the quick setting cements. Quicksands or the quick setting cements. Mostly, if you see the Fevicol, the best example is the Fevicol or that Fevibond you may buy in for 5 rupees or 10 rupees tube. And that kind of strong adhesives will also fall on this category. Got it? This quicksand and the quick setting cements, they were used for making the foundation in underwater areas. Like if you want to construct a bridge along across a river or on the sea. Okay, so the quicksand or the quick setting cements they will use for making the foundation pillars initially. So these are the typical way to understand the importance of the non-Newtonian fluids under the categories of bingham plastic, pseudoplastic, and dilatant. Beyond that, there is a shear rate thickening and shear rate thinning over there. They are being considered with respect to the time variation. Okay. All right. So far we have focused on the concept of the fluid, its definition, the way how we have to consider the shear stress, and the importance of Newtonian and non-Newtonian fluids. Now we have to focus on the units and dimensions, which is very important to account the quantitative measurement of fluid. So the primary quantities which are referred to as the basic dimensions here, nothing but we already focused in our international standards. We call it as SI system, such as mass, length, time, and temperature. Mostly whenever we focus on a particular property variation of a fluid means that is being measured with respect to the variation in temperature. Otherwise, mass capital M, time capital T, length capital L will accounts as the fundamental quantities for our units and dimensions. Particularly, this is said to be the dimension. The corresponding units will be for mass means it is in kilogram, length is measured in meters, and time always accounted in seconds in whatever the system we follow. We call this as the MK system, meter, kilogram, second system, as our international standards, or the SI system. Beyond that, we have FPS systems, CGS systems, and so on. FPS means foot, pound, and second as the measurement of your length, mass, and time. CGS means centimeter, gram, and second as the measurement of length, mass, and time. Particularly in our country, India, in the beginning of our industrialization after the independence, we followed the British standards, which means the foot, pound, and second system only we followed and developed all our industrial things. But nowadays, we are being the globalization market, so we are using our own standards and by following the international standards too in terms of mass, kilogram, and seconds, because that is mandatory to show who we are to the globalization market. Got it? So this dimension system is known as the MLT system, where it can be used to provide a qualitative description for the secondary quantities or the derived quantities. Because these mass, length, and time are the fundamental quantities. So based on that only, all the derived quantities will be considered. So for example, if you want to measure the velocity of a fluid particle to understand the concept of shear, velocity is a derived quantity as a combination of length over time. Got it? Likewise, the density. Without density, we cannot say the existence of a fluid. So it is mass over volume, which means m over L cube it is. Got it? So as I mentioned, in some countries, in the place of mass, they use the force, because force is a derived quantity of mass from the Newton's second law, said to be force as mass time acceleration. And here are some of the examples to understand the importance of dimensions. Got it? A kinetic equation of velocity in a uniformly accelerated body, which means it is already accelerating with the initial velocity of v naught, and how it varies with the time on the acceleration is related here as v is equal to v naught plus at. A straight line equation, almost it's a straight line equation when relates to velocity and time with the y-intercept of v naught and the slope as your acceleration. Under the gravitational field, it also accounts your g as 9.81 meter per second square. So in terms of the dimension, if you express, means it is expressed as L divided by T, or Lt raised to the power minus 1, which is equal to the same for the initial velocity. And the acceleration, as I mentioned, it is meter per second square, which means L divided by T raised to T square. And actually the time has the dimensions of T. So we say this as a dimensional homogeneity, an equation whose left hand side and right hand side must have the same dimension. Otherwise, we cannot use this equation in a future application. Likewise, if you want to add two quantities, they must be dimensionally homogeneous. That's what our right hand side expresses. Okay. And another example is understanding the free vibration of particle. It can be simulated by the differential equation. Nothing, it is mass time acceleration, like our definition of force from the Newton's second law, and likewise plus k times x, which is the force exerted by a linear spring actually. Got it. Force exerted by a linear spring, and the first term will be the force exerted for a either for a moving piston on a cylinder like a dashpot, which accounts for the movement of the liquid which is being handled in it, or the gases. Got it? So where m is the mass, u is the velocity, and t is the time, and x is the displacement. Which means this is an equation which represents the force balance along with the dashpot and the spring over mass of the moving object. Because the first term will also account the mass of the moving object. Okay. So, if you want to define the dimension of a unknown stiffness of the spring or the stiffness variable K, we can use this concept of fundamental dimensions and the dimensional homogeneity, and we can get the dimension of the spring constant as mass divided by time square, which means kilogram per second square. And apart from that, the primary quantities we may focus on the engineering will be the current and the luminosity. Mostly we don't use this one because our fluid mechanics will utilizes the mass, length, time, and temperature to completely understand the concept of fluid mechanics. Got it? Now the derived quantities. Some of the examples which I have been mentioned here: actual velocity, acceleration, force, energy, power, pressure, density, specific weight, relative density, viscosity, and surface tension. Most of these are the properties and the essential variables to understand the fluid and the fluid mechanics. All are said to be the derived units and their corresponding SI units. Got it? Say if you want to define a pressure means you have to measure that one in terms of the pascals. Got it? So 1 kilopascal is 100 pascals, or we may use the same for the measurement of stress too by following the Pascal's law. It is to honor the uh, Pascal, the man who gave the concept of the pressure to us. Likewise, the other things and all. The relative density is the ratio of the densities, so it is dimensionless, and other things and all you can see it. Okay. Now there is a unit cancellation procedure that I already explained in terms of dimensional homogeneity for the application of simple equations. Anyhow, this is the standard procedure you need to follow to perform any calculations under the fluid mechanics concepts. First, you have to solve the equation algebraically for the desired terms. Then you have to decide on the proper units of the result, and you have to substitute any known values including its units. Then afterwards you have to cancel units that appear in both the numerator and the denominator of any term, or commonly applicable on the right hand side and the left hand side. You can take out and cancel each other. So you have to use conversion factors to eliminate unwanted units and obtain the proper units, which is given in the previous step 2, which means that decide on the proper units of the result. Then only you have to perform the calculations to get the results. This is the simplest example to measure the force. If the mass and the acceleration is given to you, then you can follow a physical law like the Newton's second law, and you can find the force as mass times acceleration. Got it? Now the properties of the fluid. As I mentioned already, without density and viscosity, you can't imagine a fluid is you can see or believe. Okay, so the density is well known for us as a mass over volume, and the typical values is water, which has a 1000 kilogram per meter cube in SI units, and air at standard temperature and pressure. If you measure by using your perfect gas law, you will get the air density as 1.23 kilogram per meter cube. Now the specific weight. What is weight? If anybody asks about your weight, how do you say? We say it as 80 kilogram or 70 kilogram is our weight. It is in the with respect to the gravitational field or the acceleration due to gravity which is existing in the planet Earth. So always weight means mass times acceleration due to gravity, which means your force will become sometimes to be accounted as weight. It is said to be the weight force. That is how we are being, our body weight is being measured. So specific weight means you have to divide that weight by volume. So think it, mass time acceleration due to gravity divided by volume. Then what is mass divided by volume? Density. So the specific weight is density times acceleration due to gravity. For our standards of liquids and gases, water holds 9814 Newton per meter cube because acceleration due to gravity is 9.81 approximately. Likewise, when you multiply the air density that I have shown in the previous slide by acceleration due to gravity, you will get it as 12.07 Newton per meter cube. Then the specific gravity, you know it. It is the ratio of the density or the ratio of the specific weights of a substance along with its standard substance at a standard temperature of 4 degrees Celsius. Usually this concept 4 degrees Celsius which is accounted as a standard temperature, but when we go for our laboratory measurements we will go for the normal temperature and pressure. So we look into either 20 degrees or 25 degrees as the standards for measuring the density or the specific weight of a substance along with our standard substance as water for all liquids or air for all the gases. So it is a dimensionless quantity. And here is the example to measure the density, specific weight and specific gravity of the oil. So they have given a reservoir of oil as a mass of 825 kilogram and in the reservoir as a volume of this. So density means mass over volume, you will get 900 kilogram per meter cube. Specific weight means same, the density times the acceleration due to gravity. So 8829 Newton per meter cube you will get. And the specific gravity means, we know that for water at STP condition, see 998, but approximately we can use it as 1000. Okay, so the density of the oil which is filled in the reservoir divided by the density of water comes as 0.9. As I mentioned already, the viscosity is the second major property to understand a fluid as a real. Okay, so that is what it has been given here. This all occurs due to the shear or the cohesion and interaction between the molecules, which offers resistance to shear deformation. If you say density as an action, viscosity will measure the reaction. Got it? Viscosity measures the reaction. So different fluids deform at different rates under the same shear stress. That's why the ease with which a fluid pours or flows is an indication of its viscosity. Fluid with high viscosity deforms very slowly. Fluid with a low viscosity deforms very fastly, like a syrup which deforms very slowly, and for water which deforms very fastly with the change in the viscosity in their nature. That is why the viscosity is also known as dynamic viscosity. Typical value of water is, when you say the density of water is 1000 and 1 divided by 1000 will be the approximate value of the viscosity of water at its STP condition. But I think this value is given under NTP conditions for both water and air. Then the kinematic viscosity is the ratio of viscosity to the density. Got it? Generally, the viscosity of liquids decreases with increase in temperature, but for gases, it acts oppositely. So, likewise, the kinetic viscosity too. Got it? And it has the units of meter square per second, which means it has the dimensions of L square T raised to the power minus 1. Okay, in some cases or in important cases, particularly in a refinery industries, we use the concept of kinematic viscosity everywhere to account the behavior of the refinery fluids. Got it? The bulk modulus is another measurable and important property of any fluid because it accounts the nature of the compressibility, because all fluids are compressible under the application of external force, and when the force is removed they have to expand back to their original volume. Okay, so the compressibility of fluid is always expressed by its bulk modulus, which is defined or described as change in the pressure or the force. Pressure is force acting on a uniform area. Okay, with respect to the volumetric strain. Strain is the difference in the volume. Okay, which means change in the volume divided by the original volume. So that the strain is a dimensionless quantity here. That's why if you look into the bulk modulus K, it holds the units and dimensions of the pressure or the stress where it is being applied on a fluid to measure its compressibility. That's what the equation also represents. Got it? Change in pressure over del V over V. The negative sign indicates that pressure decreases in the direction of compression. That is the importance of the negative sign. Okay, or the change in volume also decreases with the initial volume to the final volume. That also another significance for the negative sign. Then another important property is the vapor pressure. This is the property which decides what we can say when a fluid undergoes, a particular liquid undergoes a phase change means this property will tell us the nature and the complete description of how the phase change occurs when there is a change in temperature or the pressure. Suppose if you have a liquid in a closed container and its subject is subject to a partial vapor pressure in the space above the liquid, which means to the top lid of the closed lid or container, and how much portion the liquid is filled. Above the free space, there is a space. That is due to the escaping molecules from the surface. So that molecules will give a minimum pressure to hold that liquid in that container. Once based on the space or the height, sometimes it reaches equilibrium when this pressure reaches the saturated vapor pressure. You know the meaning of the saturation and all, the final stage of any fluid which is holded in a vessel, because it depends on the molecular activity, which is a function of temperature. So the vapor pressure of fluid also depends on its temperature and increases with it, as we know it by the simple perfect gas law concept. Pressure is directly proportional to temperature. If the pressure above a liquid reaches the vapor pressure of the liquid, then the liquid begins to boil. This is the fundamental example. Even we can bring a liquid to boil at a room temperature by reducing its vapor pressure. That's why there is a engineering significance which always focus on the vapor pressure. Suppose if you want to pump a fluid from one place to another place through a pipeline, okay, then you have to take care that the pumping pressure should not be below the vapor pressure of the liquid. Otherwise, there is a possibility of formation of local boiling and a cloud of vapor bubbles in it. Got it? That's why I have chosen the pump as one of the closed hydraulic system here to explain. So when those vapor bubbles forms means they go and hit the possible moving metallic parts of the pump, say the propeller, okay, or the impeller of a turbine, a reverse action. Got it? What happens is it will go and hit means it first creates a noise and makes a disturbance on the regular speed of rotation of either the propeller or the impeller and cause a physical damage. We call it as erosion, metallic erosion we call. So which will not allow the proper performance of pump, which means the pumping speed and the other possible energy, mechanical energy is to be maintained by the pump will not be maintained. We call such phenomena as the cavitation. Got it? Cavitation. That's what you can see in the points 3. So if this occur continuously means it will cause a damage to the every portion or the parts, internal parts of a hydraulic system, say a pump, impeller or a turbine propeller like that. Usually these such type of cavitations can affect the performance of complete performance of any hydraulic machineries. Okay, cause local erosion on the metallic. Sometimes it may create a the crack, or sometimes it may make that vein or the blade to break. Okay, so in hydraulic systems where the fluid is being continuously handled, we must have to avoid this cavitation. So we have to maintain a pressure above the vapor pressure every time in such systems. Otherwise, you may feel a physical damage in those hydraulic systems. And the next, I can't say it as the last because it has its continuous application in the capillary also. Surface tension. This is all unknown to us. This is based on the properties of cohesion and adhesion due to the molecular attraction. All the liquids will have it. So, due to these properties, liquids generally, this surface tension will be having an effect on liquids rather than the gases. Okay, because they offer a small it will resist a small tensile force at the interface between the liquid and the air, known as the surface tension. That's how happened in a closed container also. Above the space are filled with vapors of the own molecules, or sometimes we may tightly close those containers holding a liquid with the air. So on the free surface particularly, or on the interface of gas and liquid, there exists a small tensile force as a resistance, and that is said to be the surface tension. It is usually mentioned as a force per unit length. Okay, got it? So the reason for the existence of this force arises from intermolecular attraction, already mentioned. Okay, so a molecule is surrounded by another molecule, and intermolecular forces are symmetrical and sometimes in equilibrium. So at the surface of the liquid, a molecule has this force acting only through 180 degree. We always focus on the 180 degree concept only, 0 to 180 degree, either in upward direction or in a downward direction. We will focus. Okay, so that is what shown in the figure. There is such type of tensions will cause a slight deformation at the surface of the liquid, the meniscus effect. If you are practicing pipetting out, say 10 ml of a standard solution or standard liquid, you can focus only on the lower meniscus on a capillary tube after the bulb which holds the 10 ml of volume. So even for a simple pipetting out a liquid for doing our titration and or other measurement of standards, this concept has its wide application. So this is what an example for it. Say a simple needle which is floating on a water will cause the surface tension. That's how in olden days the wooden logs, which is cut on the forest trees, will be transported through the flowing water river from top or the higher end to the bottom or the lower end to avoid the other unnecessary transportations. Likewise, the spherical shape of the dewdrops, the raindrops, whatever it is, and the rise or fall of a liquid in a capillary tubes are the results of surface tension. Even if you see a thermometer which is handled by a doctor, mercury thermometer in, I can't say the olden days, some few years back, you can feel the rise of mercury to a known level of temperature measurement in it to decide whether our body's temperature is under the proper way to diagnose. So the surface tension is usually very very small when compared to the other forces of fluid which is flowing. Okay, see for water it is 0.0728 only. So this is how the surface tension is being measured, and a simple force balance only it is being applied here. Got it? 2 pi r is the circumference of the droplet times the surface tension, which is equal to the pressure drop which is felt inside the droplet times the area. Okay, the circular portion of the area, because the projected area of a sphere is always a circular. So when you go for the simple thing, you can account the pressure drop also by measuring the surface tension. That's what it is shown here. Lastly, the capillarity. Always the surface tension leads to the phenomena known as a capillarity, when a column of liquid in a tube is supported in the absence of an externally applied pressure. As I mentioned, pipetting out a standard solution which we had in conical flask to carry out our titration and other things and all. Likewise, when you think if you want to drink a juice over a straw, this capillarity also matters there. Okay, right? So the rise or fall of a liquid in a capillary tube is caused by the surface tension of that specific liquid, depends on the relative magnitude of cohesion of liquid and adhesion of the liquid. As I mentioned, yeah, less viscous fluid will easily rise in a capillary tube. High viscous fluid takes some time. That's why when you drink a water through a straw, you can suck it easily. But think about a juice. It takes time based on the nature of the juice. Likewise, only everything is there. So capillarity is important when using tubes smaller than 10 millimeter. That is what we follow in pipetting out. Micro pipettes, the regular pipettes, all will use the concept of capillarity even to measure the standards of volume that we used for further analysis like titration. For tubes larger than 12 millimeter, capillarity effects are negligible, which means 1 centimeter hollow, straight cylindrical or vertical cylindrical tubes will have this effect. So this is what shown here with respect to the water. We have to focus on the lower meniscus, because water is a highly viscous fluid and mother of all the liquids. And mercury is another extreme, which is a liquid metal. So when you want to think about the measurement of capillarity or surface tension for mercury, you have to focus on the upper meniscus part. And here is the concept of measuring the capillarity as a height. Okay, height of capillary rise is a function of your shear stress sigma and the specific weight of the liquid we use, the gamma. And along with the radius of the meniscus or radius of the tube, it should be maximum 1 centimeter, 0.01 meter. And the contact angle you can measure based on the formation of lower and the upper meniscus from water to the mercury, because water has a specific gravity of 1 and the mercury has a specific gravity of 13.6. That's why it is said to be a moving liquid metal. Got it? So that's it about our presentation, which focus on the theory part of it. And here are the few examples to account again the same which is being expressed here. along with the measurement of the capillarity and the capillarity rise for a water surface on a 3 millimeter tube, as highlighted here very clearly. So that's it about our complete explanation of understanding the fundamentals of fluid and their properties. Okay, so this is how we come to summarize our presentation. Understanding the fluid, the difference between the behavior of fluids as liquids and gases, Newtonian and non fluids, so very clearly understood engineering units, and the fluid properties in a detailed manner, and discussion on the importance of the vapor pressure and the existence of surface tension, particularly on a liquid, and its extension towards the capillarity phenomena. So that's it. Hope you guys have understood the fundamental concepts of fluid mechanics for chemical engineering. Thank you very much, guys.